Computational fluid dynamics simulations are too slow for real-time applications, and generating them at scale is prohibitively expensive. This paper presents a method that builds accurate surrogate models for fluid flows without using a single data point from traditional simulations. Traditional CFD faces a threefold challenge. The Navier-Stokes equations are computationally intensive. Complex geometries demand careful meshing, and applications requiring hundreds or thousands of simulations become infeasible. The authors ask whether we can bypass simulation data entirely. Their answer lies in teaching neural networks the physics itself. The method constructs a structured deep neural network that embeds boundary conditions directly into its design. Instead of learning from simulation outputs, the network trains by minimizing the residuals of the Navier-Stokes equations themselves, using automatic differentiation to enforce the governing physics at every step. A crucial design choice emerges from their experiments. Treating boundary conditions as soft penalties in the loss function produces inferior results. Hard-coding these constraints into the network architecture itself ensures the model respects the physics exactly, delivering unique and accurate solutions. The authors tested their approach on hemodynamic flows, including pipes, stenoses, and aneurysms, varying both viscosity and geometry. The network learned these scenarios with remarkable accuracy, capturing nonlinear fluid dynamics in geometries where traditional surrogates would struggle. The computational gains are striking. By avoiding the expense of generating thousands of CFD simulations for training, the method achieves faster uncertainty quantification and opens the door to real-time deployment where traditional approaches would be too slow. The method has boundaries. Current demonstrations focus on 2D hemodynamic flows, and extending to full 3D industrial-scale problems requires further work. The authors note that hybrid models blending physics constraints with partial simulation data could refine accuracy where data is accessible. This work redefines what surrogate modeling can be. By eliminating dependence on expensive training data, it empowers engineers to explore design spaces, quantify uncertainty, and deploy models in real-time contexts where traditional CFD cannot follow. Physics itself becomes the teacher, and the network becomes the student who never forgets. When the equations become the data, simulation becomes optional. Visit emergentmind.com to learn more and create your own research videos.